Welcome to the Tech Talk on hot isostatic pressing from Aalberts Surface Technologies. The presentation is divided into 4 parts. We will start with an introduction to HIP. What is HIP per definition? How does it work? Which benefits brings HIP to the properties of a material and different fields of applications? Then in part 2 and part 3, case studies will follow on the use of HIP for cast and additively manufactured parts. Animation, we can see a volume element out of a solid component. We can easily detect spherical shaped defects present in the component. While performing HIP, we apply simultaneously a high pressure gas and an elevated temperature. This takes place in a HIP unit, which can be simplified as a specially constructed vessel with a furnace implemented into it. The pressure applied isostatic, meaning from all directions, because it is developed with a high purity gas. Under these conditions of heat and pressure, elementary processes in the material are activated, causing the internal defects to collapse and weld up within a solid body. Let's take a closer look onto the HIP parameters and associated mechanisms causing the shrinkage of internal defects. In HIP, the temperature and pressure can reach values of up to 2000 degrees C and 207 MPa, meaning that we apply a pressure that is higher than the yield strength of the material at HIP temperature. An inert gas, usually argon, is used as pressure medium, acting on all surfaces and in all directions. It can be seen here on the example. A combination of plastic deformation, creep mechanisms, and diffusion can be identified as mechanisms causing the elimination of internal defects, having no connectivity to the surface. In the end, a component that has been treated via HIP shows isotropic properties. HIP can be used for different types of materials and manufacturing routes, which I will explain later in more detail. First of all, I want to show you an example of how HIP can help to remove internal defects of your component. We have a practical example of what HIP can do. These are cross sections where the left one is referenced as non-HIP treated, so we can see a big artificial void inside. These two halves have been welded together. And then in this cross section here you can see the shape of this big artificial void. And here after HIP we see the right one was an identical sample to the left one but has been HIP treated. So now we can see that the big artificial pore is gone that was here in the middle. But also we can see some deformation to an hourglass shape on the right sample. That was densified by HIP, and this is because the internal pore was such a big pore, and the material of course has to come from somewhere and has to go to somewhere, so into the middle of the big cavity. So the potential dimensional change depends of course on the volume percentage of porosity. And you can, by a rule of thumb, estimate that 1% porosity refers to 1% shrinkage by volume. Of course, the shrinkage is evenly distributed if porosity is evenly distributed, and to most of the manufactured parts, of course, the porosity is evenly distributed. And since we have not such big porosity, then you can also say that the dimensional changes are not that significant that you have large deviations in your geometry. Of course, it's a really extreme example here on that slide. And as announced the slide before, and with the knowledge we have already gained here, we now want to assess in detail why HIP is performed and what are the resulting benefits of a HIP treatment. Manufacturing techniques such as additive manufacturing or casting introduce internal defects in your component. These defects can be lack of fusion defects in powder bed fusion laser beam or electron beam melted materials, residual sintering porosity in binder jet or metal injection molded parts, solidification shrinkage or microporosity in castings or AM parts, gas porosity, or internal cracks. In general, an internal defect is always associated with stress concentrations and cracked initiation points when it comes to dynamic loading of a component, as can be seen here in the 2D cross-section, where a pore is highlighted and a crack is initiating at it perpendicular to the load direction. Defects or porosity impair the surface performance and the reliability of your component. And this we can counter with HIP. The resulting benefits of a HIP treatment are highlighted on the following slide. It is obvious that the elimination of internal defects later gives less stress concentration and correct initiation points. This circumstance is highlighted on this computer tomograph here of a titanium 64 alloy. On the left hand side we have the powder bed fusion as built condition, where pores are highlighted in red in the volume, and the same specimen after a HIP treatment, and we see that there are no pores present anymore. Therefore, we can expect superior material properties such as an improved ductility and fracture toughness, better creep properties, but most importantly, significantly increased fatigue properties when it comes to dynamic load in combination with porosity, because always in dynamic loading, porosity is really a weak spot and has a negative impact on the fatigue life. But also we have a reduced property scatter, because the natural variation in defects between components is eliminated, and therefore we have more predictive properties. This is really important for additive manufacturing, for instance. But also we have an improved quality of machine polished surfaces, because you can imagine a pore shortly below several micrometers under the surface can have also a negative influence on the surface quality when it comes to polishing. And this is really important for medical applications, for implants, when it comes to sliding surfaces, for instance. On this slide, several applications of HIP are summarized. Especially a number of applications, or most important applications and aims of HIP, are shown together with typical examples of materials in each case. The first, the particular case of densification of castings or additively manufactured parts, will follow later in this presentation in more detail with examples. Furthermore, HIP can be used to consolidate encapsulated powders in order to achieve full theoretical density and to avoid segregation and excessive grain growth. Typical materials are high-speed tool steels or metal matrix composites or magnetic materials. Another exciting application is interface or diffusion bonding. It is applied to diffusion bond similar and dissimilar materials, overcoming problems of conventional joining and uniaxial diffusion bonding techniques. A typical application or case are multi-layer material structures, for instance for heat-resistant panels, but also to consolidate or densify plasma sprayed coatings. Following slides, we want to assess the impact of HIP processing on microstructure and properties with practical examples. We will start with cast turbine blades used in the most demanding region of aero engines or stationary gas turbines. Nickel-based superalloys are used as blade material in gas turbines. In service, they have to withstand a complex regime of static and dynamic loads at high temperatures. These complex-shaped blades are manufactured via investment casting techniques. However, during dendritic solidification of blades, porosity forms in the last solidifying areas due to the liquid-solid volume contraction. And you can imagine when you have this type of complex loads at high temperatures, like static and dynamic loads because of the high centrifugal forces during the high rotational speeds, the startup and shutdown of the engines or vibrational stresses, that pores are really a big issue here. And therefore we want to show you an example now with some micrographs where you can assess the impact of a HIP treatment on these type of materials. We can see porosity in a 2D scanning electron micrograph of a cast nickel-based superalloy. Pores are these spherical to irregularly shaped black dots in this cross-section. In 3D, via computer tomography, we can see the spatial arrangement of pores in the volume. The pores that we see in 2D as black dots appear here as bluish, greenish, colorized dots in the volume. And you can already see these networks of pores in the volume. In order to get rid of porosity in turbine blade materials, a special HIP recipe is carried out. And its impact is illustrated on the next slides. On the left-hand side, we have the same micrograph as seen in the slide before, but in addition we have evaluated the amount of porosity in the 2D cross-section. In order to assess the influence of HIP, the same specimen is now shown on the 2D cross-section after HIP. Via SEM in combination with quantitative metallographic evaluation, the beneficial effects of a HIP treatment is now demonstrated. The porosity is completely gone, and we now have obtained a virtually defect-free microstructure having only 0.002 area percent of remaining porosity. And now, of course, we are very much interested in the effect of having no porosity on the mechanical properties of our component. Now we are interested in the impact of HIP on the mechanical properties, in particular on the dynamic and static loading. We compare the fatigue properties and the creep properties of a titanium alloy that is used in gas turbines. We compare the as-cast condition having porosity with the HIP-treated condition having no porosity. And what we can see is a significant improvement in the lifetime of our parts after a HIP treatment. We have generated a really stress-resistant material with improved lifetime, where crack initiation is much more difficult. But most importantly, we have also predictable properties now, because scatter is much more reduced when a number of parts is being tested. Now we have learned in general what benefits a HIP treatment brings with it. And on the following slides, we want to learn how additive manufacturing and hot isostatic pressing can be a perfect match for the future. Industrialization of additive manufacturing is speeding up nowadays. Companies are adapting AM techniques such as electron or laser powder bed fusion more and more for serial production of complex parts like turbine blades. Because normally nickel-based turbine blades are classified as non-weldable, but nowadays with preheating strategies they can also be manufactured via additive manufacturing. But there is still a big hurdle to take for AM, because a ready-to-use part directly after printing does not exist. The challenge for additive manufacturing is highlighted on this slide. Nowadays, for effective production, high printing speeds are mandatory. Simultaneously, costs shall be reduced while parts are getting bigger and improve reliability. However, the typical outcome is shown on the right-hand side. We have to deal with defects, scattering, and in the end, of course, quality has its costs. In order to demonstrate how HIP can be a key technology, we have to take a closer look onto the AM process chain itself. Within the additive manufacturing process chain, HIP can be found in the post-processing block next to other post-print processes such as heat treatment. Before we assess how HIP can be a great match for additive manufacturing, we have to take a look onto the as-built state or condition post-printing. Again, as an example, we take a look at turbine blade material, but now after printing. The as-built microstructure is unique. In comparison to its cast counterparts, the AM solidification structure is much finer due to the high solidification rates. This one we can see here on the 2D cross-section. After printing, lack of fusion porosity, cracks, trapped powder particles and porosity can be found in the microstructure. Here we have the 2D SEM micrograph and also again the black dots are porosity, but much finer now as in the cast parts that we have seen in the beginning. In order to improve the properties of our printed parts, we have to make some efforts with suitable post-process steps such as stress relieving, HIP, solution annealing, and sometimes aging too. Modern HIP equipment is an enabler for new and innovative cycles tailored to the unique demands of the as-built condition. Because in comparison to old HIP equipment, shown here in red, mostly used by the industry, new state-of-the-art HIP units allow to precisely control heating rates, implement intermediate holding plateaus, but most importantly also to set desired cooling rates, which is highlighted here in green, so it can cool down also very fast nowadays. This allows us to integrate several post-build processes into one dedicated HIP cycle in the future. Please keep in mind we are talking about stress relieving, solution annealing, HIP, and sometimes aging too. The potential benefit of this modern HIP approach is schematically highlighted on the slide. Via the conventional route, a lot of time and working capital is lost in the steps in between. We have the stress relieving, the HIP treatment, the solution annealing, and the aging. With modern HIP equipment, several steps can be done in one post-build cycle. We can, or better keep in mind again the slide before where we have this holding plateaus and these carefully selected heating rates, we can implement the stress relieving cycle, then heat to the solution annealing temperature where we simultaneously apply the high pressure, and then we cool down to the aging temperature, hold it for the desired time and cool down to room temperature. Combination of additive manufacturing and modern HIP equipment can have several benefits. It can result in a reduced number of process steps. This one we have highlighted before, because we can implement many cycle steps in one process. Therefore, we have reduced the cycle time, the downtime, and also the lead time. In the end, this results in improved process control. We just have to take a look on one process, quality control. And we have improved properties because we have virtually defect-free parts. As you can see here, It's the same as in the cast parts. We have defect-free volume now with no porosity. This also is reliable and scatter can be reduced too. And in the end, this results in saving in lead time, reduction in working capital, and energy consumption. I hope this gave you a first impression on the HIP process itself and the potential it has on the treatment of castings, but also on additively manufactured parts. I will now conclude my talk. To summarize this talk, hot isostatic pressing, or HIP, is a special process that removes internal defects. High temperature and isostatic pressure are applied simultaneously. With modern HIP equipment, heat treatments such as stress relief or solution annealing and HIP can be done in one single processing step. In the end, the material properties, especially mechanical properties and corrosion resistance, benefit from a HIP treatment. HIP works for diffusion bonding purposes, powder densification, or the healing of internal defects like porosity or cracks present in cast or additively manufactured parts. HIP has its limitations when defects are exposed to the surface, and in some cases, for some inexpensive materials, HIP may not be cost effective. Thank you very much for listening to this presentation. In case you have further questions which are related to HIP or the HIP technology itself, please do not hesitate to contact me. You can find my contact details on the homepage of the Knowledge Sharing Center.